All right, so sapling number 6, this is a retrosynthesis multi-step kind of thing. So you have this, essentially what you're doing is you have ethylbenzene and you have this bromine somehow end up on the outside carbon. So let's number our carbons. Let's go 1, 2, 1, 2, and this is going to require some retrosynthetic analysis. So it's too hard. There's too many steps here to go from here right to here. So you kind of got to go back one step at a time. So if you look at this is a bromine on the left substituted carbon between these two. And usually the ways we know how to add bromines, they involved pi bonds, alkenes. So a good guess would be that this was originally, one step back, was probably an alkene. It came from an alkene. It was from a styrene. So again, now we're back to that alkene. So number my carbons 1 and 2. And then this is kind of a weird way to think about this, but how do we make alkenes? Well, the only way to know how to make alkenes is actually is to make a pi bond, obviously. And to make a pi bond, you need to do an elimination. And to do an elimination, you need a good leaving group. So to have a good leaving group, we don't actually want to go backwards. We actually want to think about a place to have a good leaving group would actually be in the benzylic position. So when we initially looked at this, we probably should have thought, well, it's going to be pretty easy to put a carbon or bromine on carbon 1, right? So basically it's kind of like a do-si-do, trying to put the bromine on the less substituted when it normally wants to be on the well substituted. So to make a pi bond, we need a good leaving group. And do we know how to put a bromine in a benzylic position? We certainly do. And so that goes back to here from our starting material. Now, there's a couple different ways to do this. These are all like radical reactions. These are the ways to do the radical brominations. So this first one going forward would be that Br2 and lighter energy. If we're going to do an elimination here, we're always competing with SN2, so we want to have a really big bulky base. So one of our big favorite bulky bases is that tert butoxide. And then to get the bromine on the less substituted side, that was that HBr and peroxides, which might be one of those ones you kind of forgot. This is that anti-Markovnikov kind of way to add bromine to the less substituted carbon. Yeah, so just to remind ourselves of the Br2 itself is relatively a good electrophile, but there's nothing here that makes this species is pretty stable, right? So you need the light to really break this Br bond, and then that's what makes this benzylic position willing to also break a CH bond and make that radical that's stabilized by this. So you kind of need that little bit of energy to push over the edge to initially break the Br bond, that initiation step. And then those Br radicals will take off a CH here, then another one add in. But yeah, you need that energy first to get it started. The other, make sure your eliminations are tough, and then obviously same type of deal over here. But again, these are, for these kind of tests, they're not requiring mechanisms. They're requiring you to understand where things go. I mean, mechanisms always help, but understand where things go is really important too.